So welcome the series lectures of design of machine elements. So in today's lecture we are going to discuss on the design of cotter joints against the static load conditions. So during this lectures we are find out the various failures in the different elements of the cotter joints, and the objective of today's lecture is study the various failure which are present in the cotter joints based on the external loads. And the outcome of these lectures, after completion these lectures, students are able to design the cotter joints for the various applications. What is the cotter joints? So cotter joint is used to connect two coaxial rods which are subjected to either axial tensile forces or axial compressive forces. It is also used to connect a rod on one end side with some machine parts like crosshead or base plate on the other sides. It is not used for connecting shaft that rotate and transmit the torque. Is very important. It is not useful for the rotating members. It is only for the steady conditions, for tight the two conditions. The typical application of the cotter joints are like as joints between the piston rod and the crosshead of the steam engines, then joints between the slide spindles and the fork of the valve mechanisms, even joints between the piston rod and the tail or the pump rods, and it is also used in the foundations bolt. So means you can just apply the tensile forces or the compressive forces for these cotter joints, and it is useful for only this direction. It is not useful for the rotations conditions. So for the cotter joints, the three basic element is present for the cotter joints. So this, the cursor is indicate is the socket, then the middle part is called as the cotter, and this end part is called as the spigot, and these two ends is connected with the spigot, and the socket is the rod of that the extension member. It may be the wire rope, it may be some bar, or it may be some another element is connected with the end of the socket and the spigot. And the cotter having the one side is perpendicular with the direction of the force, and one side is a slant with that direction of the support, and the slant is called as the wedge. Is the wedging action is present. What is meant by the wedging? The principle of the wedging actions is to used in a cotter joints. A cotter is a wedge shaped like this, so means is a perpendicular with this force direction and is inclined with that forces. And this wedging action, a cotter is wedge shaped piece made of the steel plates. The joint is tightened and adjusted by means of the wedge actions of the centers. The construction of this cotter joint used to connect the socket and the spigot, and between that gap you can insert this cotter. So is a typical engineering drawing of this cotter joints. There is a spigot, cotter and this pocket, and is the assembly side view of this two, and the various notation is given for this cotter, spigot and the sockets. So here d1 is the diameter of the socket is mentioned. D1 is the diameter of the socket, this one. Then D4 is the diameter of the socket collar joints. So is a D4 is the cotter socket joints is mentioned. So this one is the D4. Then C is the socket collar end thickness is given is a 0.75D. The thickness of the cotter T 0.31. Thickness T1 is a of spigot cotter. Then D3 is the diameter of the spigot collar. T1 is the thickness of the spigot collar. A is the thickness of the cotter end, and B is the width of the cotter, and the C is the clearance. So these are the various notation is present for these cotter joints respective for the spigot, cotter and the sockets. So based on this notations and based on this nomenclatures, our aim is to find out the typical cross sections where this element is failed, and after this assembly we are apply this some external forces. The notation is given the P, and based on that P our aim is to find out the area where it's failed. So starting with this spigot, so is a free body diagram of the spigot is given. So this a separate forces is present on this pivot, there is having the tension forces P this end as well as this end, right? And what will be happens if the tensile forces is present on this? So obviously, where is the minimum cross section area is present, and at this typical cross section area, the spigot will be fail. So maximum area of this is a D, is a spigot joints and is collar joint. So means collar is not fail. Maybe the failure occur in the spigot diameter, either maybe the failure occur in the minimum cross section. So obviously, so is a hollow cross section is present where we are going to insert the Cotter insert hollow cross section, and is a typical cross section area is there, and the failures occur at the typical zone of this cutting portions. So is the area where the tensile failure is occur. So our aim is to find out the area. So D2 is the diameter of the spigot and T is the thickness of the Cotter. So our aim is to this red color is indicate the cross sectional area where the tensile failure is occur. So our aim is to find out the cross section area by using this equation. So pi by 4 D2 square is the diameter of the spigot minus the area of the Cotter we are going to insert is minus D2 into T. So is a cross sectional area of that spigot. So we can find out the tensile failure sigma T is equal to force per unit area and is a cross section area. Then we are coming on the spigot is also fair by the shear failure, and the shear failure occurs at the plane which is parallel with the force directions. So is the plane this side and the back side of this support is the shear failure is occur. So these are the two zones. This color gray color is indicate this shear failure zone. So our aim is to find out this. So is the D2 is the diameter of this spigot and A is the thickness of this distance which is from the surface of the spigot and the surface of the Cotter. So you can find out this cross section area. So is obviously D2 into A plus D2 into A. So means twice D2 into the is a typical cross section area for the shear failure. So you can find out the shear failure tau is equal to force divided by the cross section area. Then we are coming on the spigot crushing failure. So here, so this is a zone where the total forces acting on that the surfaces, and due to that forces maybe this zone will be crushed or it will be pushed in that opposite directions. So it may be crushing due to that forces, and you can find out the crushing area and is equal to D2 into T. So the sigma C is again you can say the P divided by the A. The crushing stresses is always equal to the tensile stresses in some static load conditions based on the some application. So is the CS cross sectional area sigma C is equal to D2 into T is the area, and sigma C is equal to force divided by the cross section area is a D2 divided by T. So these are the three failures occurs in the spigot. Then we are coming on the socket of that the Cotter joints elements. So is the typical joint is the diameter of this rod, the diameter of this socket, and then there is the hollow portions for the insert the Cotter. Then inside that this hollow portion is D2 is indicate the diameter of the spigot end. So the cross section is minimum cross section is present at this particular plane, and when we apply the tensile forces this area will be fail, either this cross sections is getting in failure conditions. So is a typical here the red color is indicate and the element is fail at this cross sections. So our aim is to find out this cross section area against the tensile failure. So D2 is the diameter of this spigot, D1 is the diameter of this socket, and T is the thickness of the Cotter. So you can find out the cross section area based on the equation pi by 4 in bracket D1 square minus D2 square minus again in bracket D1 minus D2 bracket complete into T and whole brackets completed. So in this way you can find out the cross section area for the socket against the tensile failure, and you can find out against tensile stresses sigma T. So here we have found out the tensile stresses. Sigma T is the force per unit area, and the force is given the tensile forces P, and the cross-sectional area for this socket is also mentioned here. So by using this, we can find out tensile stresses present in that the socket end. Then again, based on that the tensile forces, the shear failures occurs in these sockets at the end where the total forces is present in the parallel directions of that this collar of that the sockets. So these gray colors indicate the failure of that the socket at that end, and these are the four zone is present, 1, 2 and the opposite to these are the total 4 cross section area is present where the shear failures occur. So our aim is to again find out the area where it is failed. So here D2 is the diameter of the spigot, D4 is the diameter of the socket collar, and C is the clearance of this socket collar, either the thickness of the socket collar. So by that you can find out the total cross section area where the shear failures occur. So is D2 and D4 and the C. By using that equations you can find the twice in bracket D4 minus D2 bracket complete into C whole bracket come to C is the total cross section area against the shear failure. So here you can find out the tau is the shear failure shear stresses is equal to force per unit area. Then the socket is also fails against the crushing failure is a sigma C. So there this Cotter is pushes in this collar thickness and is maybe the fail due to the crushing stresses. So this blue color indicate the cross section area where the total crushing stresses is occurs. And here you can find out that again D2 is again the diameter of this spigot and D4 is the diameter of the socket collar. So these are the area. You can the cross sectional area is equal to D4 minus D2 into T. So in this way you can find out the crushing stress sigma C is equal to force per unit area. Sigma C is equal to P divided by this value D4 minus D2 bracket complete into the T. So in this way you can find out the crushing stresses. Then our aim is to find out the dimensions of the quarters. So quarter is failed by the shear. So typically this end the collar is present for the socket and the hole is present for the spigot, and due to this collar the forces distribute in the two directions for the socket side and for the spigot side 1. So means due to these force conditions the quarter is failed at the two different cross sections based on that the load apply conditions. So here this area is there where the quarter is failed, and these are the cross sectional area for the shear failure. So in this area you can find out by using the equations. So here T is the thickness of the quarter, B is the width of the quarter. So is a B into T is a one area, again B into T is another area. So is a twice B into T is a total cross section area for the shear failures about that the quarter. So you can find out the shear failure tau is equal to force per twice B into 2 is a cross section area. Then maybe this quarter is failed due to the bending failures. So obviously based on the forces conditions the bending failures occur in this pin. So this two end the different forces is present. So suppose is a P, this force is nothing but the P divided by 2 and P divided by 2, and due to that the bending is occurs in this quarter in the like as the bottom figure. So avoid the bending failures, our aim is to find out the free body diagram first, and based on the free body diagram you can find out the maximum bending stresses occur in that the pins. So T and B is the thickness of this quarter, the P is the total load is present on that the quarter, and at this end the P by 2 is the forces. So is based on the strength of machine element you can find out the maximum bending failures occur in this pin. So in this way you can find out the total distance. You can convert these forces in the different way, P by 2 like as a UDL and the ULs. At this end the UL is present, and based on that the UL and the UDL you can find out the maximum bending stresses present in that the pin. And we know the maximum bending stresses for this pin is a P divided by 2 in bracket D2 divided by 2 plus X is the distance is stresses in bracket minus P divided by 2 into Z, and we know the total bending stress is nothing but sigma B is equal to MB into Y divided by I. So in this case, Y is equal to B divided 2 is the total height of the quarter divided by 2, and I is the moment of inertia of this quarters. So is a typical rectangular cross section is present. Based on that, you can find out the TB cube divided by 12. So you can put this all value in these equations and find out the bending stresses. So these are the various failures mode is present in that the Cotter joints. So it's a typical process for design the Cotter joints against the static load conditions. In this basic procedure, first to calculate the dimensions of the Cotter joints consists of the following step. The first step is calculate the diameter of each rod by using the equations. D is equal to under top 4P divided by pi into sigma D. So it's based on the sigma tensile stresses. The equation is convert, and you can find out the D. Means sigma T is equal to P divided by cross section area of the diameter. Means sigma T is equal to force divided by pi by 4 D raised to square D square. So in this way, reshuffle this equation and you can find out the diameter. Then second is calculate the thickness of the Cotter by the empirical relations. So T is equal to 0.31 D is the 3 times D. So D is the diameter of that the end rod. So in this way you can find out the T. Then calculate the diameter D2 of the spigots on the basis of the tensile stresses. So is P is equal to pi by 4 D square minus D2 into 2. This is equation 4.2 P is given for this here. So then when the value of Pt and the sigma T are the substitute, the above expressions become quadratic equations and you can find out this P value. Then calculate the outside diameter D1 of these sockets on the basis of the tensile stresses in these sockets by using these equations. P is equal to under root of pi by 4 D1 square minus D2 square minus in bracket D1 minus D2 bracket comes into 2 whole bracket comes to sigma T. So just you can reshuffle the equation sigma T, sigma C and tau, and based on that you can find out some value of that Cotter joints. When value of P, D2T and sigma T are the substitute, the above expressions become the quadratic equations and you can find out that the value. Then the diameter of spigot collar D3 and diameter of this socket Cotter D4 are calculated by the following empirical relations, and D3 is nothing but the 1.5 times D and D4 is nothing but the 2.4 times D. Then the dimension of the A and C are calculated by the following empirical relations. These are the clearance between the collars and the supports. A is equal to C and is nothing but the 0.7 D. Then calculate the width B of the Cotter by shear and the bending and select the width which is the maximum between these two equations. The equation is given, is based on the bending stresses. Check the crushing and the shear stresses in the spigot end respectively. By using that equation you can put this all value in that equations and check these stresses. Even check the crushing and the shear stresses in the socket respectively based on these equations. Calculate the thickness T1 of the spigot Cotter by the following empirical relations. T1 is equal to 0.45 D and the taper of the Cotter is. So means just the equation is given based on the stresses sigma T, sigma C and the tau. You can put these equations in terms of the forces based on the cross section area and reshuffle that equations based on that actual value and find out the dimensions of this Cotter and the spigot as well as the sockets, and based on that dimension again you can check this dimension safe or the unsafe. If the calculated stresses is greater than the actual stresses, then you can say the dimension is safe, and if it is not, then you can modify the dimensions. So the conclusion of this lecture is based on the short answer questions. What is the use of the Cotter joints? Why Cotter having the slant sides? And what are the different failure presents on the Cotter joints? So students, thanks for watching these lectures. In next lecture we are going to discuss on the design the different machine elements for against the static load conditions. Thank you.